Yes, yes. The type C.
Okay. All right. Good afternoon, everyone. My name is Ren Zekun. You can call me Danny. I'm from SMART, Singapore MIT Alliance for Research and Technology. I've been working with Tonio on applying different machine learning methods to different material science problems, like diagnosing solar cells, thermoelectric devices, or reading the XRD spectrum. So today I'm going to give you a brief coverage on applying Bayesian inference to device diagnostics. So I would like to motivate this talk by giving you guys a general picture, why do we need Bayesian inference? All right, so the diagnosis challenge. This is a problem associated with in the material science world. Our system is quite complex, and this is an example of a solar cell. And you see these different boxes essentially representing different parameters where you can extract for the solar cell device, and it's affecting your eventual solar cell efficiency. So what we measure typically is this, is the GV curve, the current voltage curve, either light or without light. And we can get the cell efficiency out of this GV curve, but this is not something we only care about. As a material scientist, we want to know more. If the cell is performing bad, we want to know the root causes. So essentially what we want to know is all these boxes here. But this becomes a mathematically constrained problem because the information you get from this GV curve is limited. And the values you get, and the values in those boxes is not limited to a single value. So the meaning of mathematically under-constrained problem is your input does not, your input is contains insufficient information for you to extract everything from your output. For example, you are trying to solve an equation of x plus y equals to 1. You want to know the values of x and y. That is mathematically impossible. You can only get the correlations between x and y. So what if there is an algorithm which treat its unknown parameters as probability distribution function instead of a single value, and constrain this probability distribution as we see more experimental data? So what you are seeing here, these four figures on the diagonal, is the probability distribution of 13 unknown parameters for a solar cell device, and on this graph is, as we see more and more observations from our experiments, the probability distribution of all those unknown parameters starting to converge. So it's becoming more and more constrained. So so this is actually done with Bayesian inference. It's just a way of updating your past informations. And if you see any new observations, and how do you incorporate your new observation with your past observation? So yeah, without further ado, let's introduce the Bayes theorem. So in order to perform Bayesian inference, what you need is essentially the Bayes theorem. So this gentleman here, Thomas Bayes, is known for the Bayes theorem. This is the equation form of the Bayes theorem. And if you move the denominator here to the left-hand side of the equation, this actually just becomes the joint probability of P(H) and P(E). H is your hypothesis, and E is your evidence. So it aims to answer this question, giving a new observation. What is the probability that my hypothesis is true? So the statisticians, in their language, they have named each terms. For example, the thing we care about is the posterior, and then you also need prior, likelihood, and a normalizing constant. But we can reframe that in a experimentalist language, where the prior, the posterior is nothing but a parameter estimation from your new experiment. So you run some new experiment, and what will be the likelihood of my underlying, for example, interface or bulk properties. And the prior is nothing but your prior parameter estimation from the past experiments. So what you have learned and from either literature or your past runs of experiments. And the likelihood is your forward model. So in the material science world, we always have a device model for modeling like your device, like basically everything. Like we can model like a solar cell performance, we can model batteries, we can model some electric devices. And the evidence is just a normalizing constant, so we will not really talk about this here. So now knowing the form of the Bayes equation, we actually can start with a very simple problem. We start to solve our first Bayes problem. So in this case is precursor contamination detection using EDX. So let's see like 1% of precursors for perovskite materials is contaminated in Tonio's lab. So everyone in Tonio's lab is doing a really good job, like keeping record of all your experimental details. And then we know from the experimental logbook, in all the past runs, there's only 1% of the past runs is affected by this precursor contamination. And like there's a new student who sort of developed a new recipe. So he synthesized a perovskite solar cell, and the efficiency is not good. So he's suspecting it might due to the precursor contamination. So one of the colleagues is suggesting him to run an EDX measurement. Let's say like the EDX measurement is pretty accurate. So it gives you 99% accuracy when your sample is indeed contaminated with undesired elements. But at the same time, because like the way you're handling the sample, maybe like you have some undesired elements on your tweezers, on your gloves. So even the sample is not contaminated, it can be diagnosed to be positive in your EDX test. So indeed, like he ran a test, and this precursor is shows a positive. It gives a positive test, and then what's the probability that this precursor is contaminated? So the Bayesian way of approaching this is, firstly, we will look at the past information. This is essentially our lab logbook. So this is our prior. And the likelihood is the accuracy from the EDX measurement. So it's this 99%, and also this 10%. So this term we call it false positive, meaning like even the samples, like in this case, even the samples is without contamination, you can still get positive results from the EDX. So if you write the complete Bayes term, and like the answer actually is 9%. So it's a little bit counterintuitive. Like even like the EDX is giving you a 99% accuracy in telling you like if the sample is indeed contaminated, and it will give you a 99% accuracy. But still, like essentially, like what this number tells you is like you need more measurement. So like just based on if like the student just say, okay, I ran the EDX test, it's positive, so my precursor is contaminated, I will just throw it away. But like the Bayesian is telling him actually there's only 9% that your sample is contaminated. So essentially, what the Bayesian will sort of ask the student to do is, like the EDX might not be sufficient to provide so much information for you to throw away these precursors. You might need to run additional measurement. But yeah, like this is just like a very simple example with Bayesian inference, and we can do our home base with some Jupyter Notebook example. So in this case, I will walk you through like using Bayesian inference to extracting certain parameters for solar cells. So let's say we observe a set of GV curves at a different temperature for a solar cell. So what is the ideality factor and the recombination coefficient for that GV curve. So again, the way we apply Bayesian inference is we write the Bayes formula first. So every time you want to do anything with Bayesian inference, you always write the Bayes formula, but you change your hypothesis and your observations with the actual thing you observe and the actual parameters you are trying to infer. So so here we are trying to infer B prime and N. B prime stands for the recombination coefficient, and N is the ideality factor of your device. GV is just the measured current voltage curves. And so we want to know the probability of B prime and N given this GV. So the way we do it is we write the complete Bayes formula, and this is a constant, so we don't really need. So the remaining two unknowns is the probability of B prime N, and also the probability of GV given B prime and N. So this term is called likelihood. Is essentially your forward model. So for this workshop, we will just use a standard like ideal diode model to model these GV curves. So for those who are familiar with semiconductor physics, this will ring a bell. But I can later I will explain in details. Or maybe I can explain this bit by bit. So J is the output of your measurement, the current values is a current giving a set of V and T. V is voltage, T is the temperature. So in the experiment, what you are doing is you are varying your bias voltage, you are changing your temperature, and then you are measuring your current. And in the equations, so this term actually is determined by GL. GL is the light-induced current from the solar cell. For the sake of the workshop, we treat GL as a constant, and G naught times this exponential term -1. So G naught is the recombination current, which is typically strongly affected by the temperature. So G naught is actually, so the dependence of G naught on the temperature is described by the second equation here. And N, the N in both terms is the same, so it's the ideality factor of your diode. Okay, so by knowing B prime and N, and we are experimentally vary the T and V, so we will be able to get J, right? So for every set of B prime, N, and V and T, we will get a single G current value. So that's essentially our likelihood. So that's one of the important things if we wanted to apply, if you want to do any sort of Bayesian inference, you need to specify this forward model very carefully. The other thing is prior. So remember, we don't really see any experiment yet. So we will assume this prior is a uniform distribution, meaning it will have an equal probability across the whole parameter space. Okay, so now you can go to the Jupyter Notebook. So we navigate to this AMD workshop demo folder. And there are 4 subfolders. So we are doing Bayesian. So Bayesian is a package our colleague Rachel and Giuseppe developed back at MIT. And so the goal of Bayesian is just like doing this Bayesian inference, but in a faster way. Later you will see that in the examples. And then we navigate to examples. So far so good. And then we go to diode. There are 2 Jupyter Notebook examples. One is called ideal diode simple. The other thing is called ideal diode. For this workshop, we will just go through a simple example where we just do a Bayesian inference on a really coarse grid, meaning we are not doing any optimizations for very detailed optimizations for parameters. Okay. So this example is meant to be a very self-explanatory example of using Bayes to perform a fit into ideal diode solar cell. So the overall procedure we have talked in the presentation is essentially this 7 steps. So for the workshop, we will just go from 1 to 4. So first of all, we have to define a parameter to fit, meaning like we have to define our prior. And we will use a 20 by 20 grid, so there will be total 400 points. And we will initialize a uniform prior probability distribution as we don't see any past experiments, so we just assume nothing in our prior. Okay, and then we will load the experimental data, and then we will generate we will load the forward model. So we will load the forward model, essentially our likelihood function in the Bayes theorem, and then generate the model data to compare with the observations. Then the last step, as long as we have prior and likelihood, we will be able to use Bayesian inference to compute the posterior probability, and then choose which grid, which point. Like the grid is just subdividing your parameter space. Like you have like your n values from 1 to 2, and then you're subdividing that into like 20 discrete values with a step size of 0.005 or something like that. And then like by right, like for this workshop, we just stop at step 4. So by right, what you should do is then we should choose a region with the highest with a higher posterior probability distribution, and then fine-tuning that grid, and then by subdividing the grid, then we can increase the resolution of that of your step size, and eventually you will be able to get like better fittings. Okay, so how to use the Jupyter Notebook is it's the same as what Qianxiao has shown. So you just press Shift and Enter on each cells. So this is the ideal diode model we have discussed. It's again we have seen in the slides. So the current J is a function of V and T. This is something we experimentally vary. And it equals to GL plus G naught times this term, and GL is your light-induced current. So we treat this as a constant. And G naught is a temperature-dependent term, which is described in the second equation here. Yeah, in the second equation here. And just for this workshop, we will use silicon zero temperature band gap, which is 1.2 eV. So the EG term here, EG naught. So the two unknowns in these two equations is just B prime and N. The recombination coefficient and ideality factor. Okay, so we'll start by importing some code. This is importing some Python libraries. And then we will, so first of all, like for all the Bayesian problem, we have to specify our prior. So we have talked many times. Our prior is B prime and N. Let's give B prime a range from 10 to 1,000 with a log spacing, a length of 20, meaning you have 20 data points between 10 to 1,000. And also then we can also specify the ideality factor N. So because we know it's a junction, it's a diode, typically it has a range from 1 to 2. So let's just put it in 1 to 2 with a length of 20. Okay, so we are press Shift and Enter. So we are done specifying the prior. At the same time, we also need to specify the experimental conditions. So if you are running your experiment, what you are varying? For example, in this case, what we are varying is the voltage, the bias voltage of your device, and the temperatures. Okay, so let's add the voltage and temperature into the same PL. Into the same PL, and then we can add the output. The output is a current, and it has a unit of ampere per centimeter square. Okay, so we have done that. Then, oops, I haven't. Okay, I have to shift enter this part. Okay. And then we can load the parameters PL into the Bayesian. So the Bayes model is just loading the priors into our Bayesian model. We can print out the priors. Okay, so here what you are seeing is the first 10 points in your 20 by 20 grid. So like the BP is the B prime, the B prime is the values we're gonna vary when we do the Bayes inference, and the N is it's again is also the thing we're gonna vary. And what you are seeing here, the BP is not changing because this is a 2D matrix. So we are only increasing N with a 0.005 step size. The min and the max is representing the width of your grid. And on the last column, you see the probability, which is 0.0025. That's actually, because I said like we use a uniform distribution for our prior, so they will have equal probability. So we're not making any assumptions yet. So which one is more likely to fit your GV curves? Okay, so let's add in our observations, which is the experimental measurement. Well, for the workshop, we will just use a simulated GV curves as the experimental data. So we'll use n equals to 1.36 and b prime equals to 258 as our like ground truth parameters. The reason we're doing this is we can compare like the fitted parameters with our ground truth, so we can know how good the Bayes inference is at recovering your true parameters. So in order to generate the experimental data, let's define our function first. So this define compute ID is just the coding of the previous two functions we have seen, we have go over many times. Yeah, so we specify a value of GL. This is our let induced current, and V and T our experimental conditions, and then the N and BP is just parameters we want to vary. So eventually we can get J. Okay, so we can press Shift and Enter. So on the bottom, on the bottom, what you are seeing here is the like simulated GV curves at 4 different temperatures. So let's use that let's use that as the observations for the Bayes inference. Okay, we can see how many data points we generated. We can just use the len data. So that's total 305 data points. And okay, what this step does is essentially is trying to reduce the number of data points you need to fit into the Bayes inference. So why do we need to do that? Let me explain this using this graph. So by looking at this GV curve, if you are looking, this is the x-axis is the voltage. If you're just looking at the voltage from 0 volts to 0.4 volts, like basically this region is not interesting at all. It's like a flat line with values equals to 0. So do you really want to take like many data points in this line? I don't think that's a good idea because it's gonna just slow your computation. So what this step does is essentially just get the key points in that curve. Okay. Of course, you can always choose to keep all the experimental data. So you you can just change the keep all equals to true. But let's for the workshop, let's just use less data points, so it will be faster to compute. Okay, so let's say we grab like some key points from the above GV curves, and let's see how many data points of the previous 305 were kept. So now it become 59. Okay. Then we can, so far we have specified our prior. We have loaded our experimental data. The next step is to specify the likelihood. So the Bayes theorem is like two parts, right? You need a prior, you need the likelihood. What is the likelihood? So we discussed this will be our forward model, which is the ideal diode equation. And if you go back here, the definition of compute ID, this is essentially the coding of that two equations. So that's just your forward model. You can just like load this forward model into the Bayesian into your Bayesian. Okay. So you can actually see like when you are loading, you can choose the mode equals to function. The model data equals compute ID, which is like it's a function. It's not any data. So you can actually. So this is only showing you Bayesian inference with the analytical equations. So what you can do, like for your own problem, you can attach a file or even like your numerical packages or whatever. For example, for Solar, you can use PC1D or SCAPS1D or even Centaurus. It's just like you are attaching different models in this step. Okay. And we can have a look at the model data. So we have talked about like we know in our prior we specify the B prime and N, and also we know the values of V and T. So this is something we experimentally vary, and with the forward model we will be able to compute J, right? So that's just like very straightforward computation. And what we can also do with Bayesian is you can specify your uncertainties in your measurement and also in your model. So what this step does is if you, like in the definition of the model, I actually added some experimental errors. And so like with certain values, with certain like values of current, this is the same as what we have generated, but there's an additional column called uncertainty. So it's just like with certain values of current, there will be uncertainty values assigned to your current. And you can typically see is like the uncertainty becoming higher when your current is high as well. So this one has the highest uncertainties. So okay, so now we have so far we have done the prior. We have load our observations. We have specified the forward model. Now we can run the Bayes. But so the most straightforward way is actually if like we just press Shift and Enter. The most straightforward way of running this, because we know we have a 20 by 20 grid. What you can do is just like do a brute force way of computing all the posterior probability of that 20 by 20 grid. But the problem of doing this is if you have more unknown parameters. If, for example, you are trying to infer like 5 unknown parameters, then it's 20 by 20 by 20 by 20 by 20. So the number of runs increases with O to the power n. N is your number of unknowns. So this will become really slow if you are trying to infer like many unknown parameters. So what the Bayesian does is, at this step, is just doing some sort of random sampling. So, and if like let's say like it randomly chooses a point, and then it says like the probability of that is high, so it tends to have a higher probability of staying around that point. If it's low, then it might just discard that point and then go to explore somewhere else. So by doing this, like instead of running like 400 runs, we did 38 runs. And we can visualize the results of the Bayesian inference. We can just press Shift and Enter. So I will spend some time to explain this graph. So let me make it smaller. Okay. So the two graphs on the diagonal is the probability distribution of your two unknown parameters. The y-axis is the probability. The x-axis is your parameter value. And this is for the B prime, the recombination coefficient, and this is for the ideality factors. So you can see the red points is the ground truth. So it's something we use to generate the data. So you can see like Bayesian is doing a pretty decent job of recovering the ground truth. And the off-diagonal picture is the correlations between the n and is the correlations between your two unknown parameters, your B prime and n. So you see like there are certain like linear correlations, and yeah, again the circle is the ground truth. Okay, so after seeing like 4 set of GV curves, we have generated this probability distribution of our two unknown parameters. Then we can do some comparisons. Like as a material scientist or like as a researcher, I always like to compare my simulation with the experimental data. So I will do a comparison of the plot. The blue is the observed curve. And like you have 3 additional curves with different, like 3 different B prime and n, 3 different sets of B prime and n values. And on the right hand side, this is a curve where it's comparing the delta J, essentially like in a sense it's like it's not like it's in a sense it's like your errors. We can also list out the 5 parameters, which gives you the highest posterior probability. So let's just print that out, and you can visualize what's the probability and what is the corresponding parameters. So the first column is just the posterior probability, and the B prime and n is again like the thing you extracted from Bayes inference. We could compare with let's compare with the ground truth parameters, which is n equals to 1.36 and BP equals to this value. And then we take the most probable one, so which has a probability of 0.39 with giving like B prime and n values. And then let's say, okay, the error in the B prime determination is 13%, and the error in n determination is 1.1%. So it's not, yeah, I would say it's decent, but it's not so good. The reason is like we only did like this. There are actually 7 steps I introduced in the beginning of this Jupyter notebook. So we only did step 1 to 4. So by right, what you should do is you go back to this plot, and you say, okay, I sort of narrowed down the parameter space. So I know roughly like my B prime will take a value from 100 to 500. And also my n value will be likely between 1.2 to 1.6. So I should then narrow the range of your parameter space and define, and then essentially like using like a finer grid to do the Bayes inference again. So like what the Bayesian package allows you to do is actually it does this automatically. So if you have time, I will strongly encourage you to go through the other example. So this one is the ideal diode without sample. So that one actually did so this file actually did the steps from 1 to 7. So it's a complete loop of performing the Bayes inference. Okay. The other thing I want to show, yeah, that's essentially done with. So that's essentially your first Bayes inference. This seems like pretty easy, isn't it? So what I want to show here is the complete graph of what we have done for a tin sulfide solar cell device. So it's basically the same as what we have done for our Jupyter notebook example. The only difference is which we replace the ideal diode model with a numerical SCAPS 1D model. So that model is like solving some continuity equations, like diffusion equations. But really, like, and it's just like it's more complex, but like the logic is the same. And the parameters, instead of exploring the ideality factor or recombination coefficient, we are looking at more detailed parameters like delta EC, the band offset at your interface, your surface recombination velocity, your mobility, and lifetime of that tin sulfide device. So by feeding that with GV curves at different temperature and illumination intensities, so this is again the graph we have shown. So as the number of the observations increases, we can actually see like the Bayes inference starts to update your probability, right? And at the same time, the off-diagonal matrix is actually showing you the correlations between each parameters. So you're actually seeing like there's a very strong correlation between your mobility and your tau. So the reason of that is actually because the square root of mu tau is your diffusion length. So that's something like could be explained from physics. So but the thing is, Bayesian doesn't really know all this. It's just like, okay, I just like blindly do some random sampling and I discover these correlations. If you don't really have that equations, you can actually say, okay, I found a strong correlation between mu and tau, and then I could like sort of explore what does this mu tau product means. Okay. So there are a number of ways of doing this, like searching, like just searching in your grid, in your parameter space. So like instead of doing a brute force way of looking through every data point in your grid, there is a grid search. There's also Markov chain Monte Carlo. There's also like the method I'm introducing in the Jupyter notebook is called successive subdivisions. This is the method Rachel and Giuseppe developed at MIT, and this is gonna be published soon, I think in next week. And also the website, they also have a website for this Bayesian. Okay, so yeah, that's basically my part. Any questions?